Good morning everyone. So in this today's class we are going to discuss the instruction format. Instruction format of computer architecture. As we know, any processor is executing millions of instructions per second. Okay? The instruction may be the system instruction or user defined instruction, the user programs which are going to execute by the processor. Okay? So we are going to learn the instruction format of a computer program. So instruction is basically classified in these 5 types, that is 3 address, 2 address, 1 and half address, 1 address and 0 address instruction. We know that instruction is a combination of operation code and the operands. The operands is basically the data which is executing by the output. Okay, and the operands are basically resides in main memory or reside in different type of register or different type of accumulators. So in the first case, the 3 address instruction, as the name gives us examples, that the 3 address means there are 3 addresses the operands is residing. For example, in the first example, that add R1, R2, R3. So here there are 3 registers R1, R2 and R3. The content of R2 and the content of R3 is added and the result will be stored in register R1. Here in the green line we can see that the example, the register R1 contains the value of register R2 plus register R3. The addition value will be stored in R1. Or add ABC. Here A, B, C, these are the memory addresses. The memory of the main memory. Actually, it is residing in the main memory. So, main memory content of memory B and memory C will be added and the result will be stored in memory A. So, here 3 addresses will be used, register or 3 memory locations. So, this is why it is called 3 address instruction. In the second case, that is the 2 address instruction, only 2 memory addresses will be used in this instruction format. For example, add R1 and R2. Here, register content R1 and register content R2 will be added and the result will be stored in the first register, that is register R1. Similarly, in this case, add A, B. A and B are the memory location of main memory, that is RAM, and the main memory content of memory location A and main memory content of memory location B will be added and the result will be stored in main memory location A or variable A. So here 2 addresses is used, so it is the 2 address instruction. In the first case, there are 3 addresses used, so it is called the 3 address instruction. In the third case, we call the 1 and half address instruction. Why it is named so? Because here the combination of memory register and combination of main memory will be used for the operation. Here R1, all the cases R1, R2, R3 defines the content of registers and A, B, C, these are the memory locations in main memory. So 1 and half address is called because memory register and the operation is defined with the main memory locations. For example, add R1, B, that is memory register contents of register R1 and the memory location B will be added and the result will be stored in register R1. So here you can see that R1 plus memory location of B will be added and the result will be stored in R1. In the fourth case, 1 address. Okay? So 1 address means just for example add R1. Add R1 means register R1 content will be added. Added to what? Added to the content of the accumulator. Okay, what is accumulator? Accumulator is a special purpose register which contains in the CPU, inside the CPU, and the accumulator contains the intermediate value of a program. Okay, if the does not contain the final value. Actually, it is the intermediate value of a program. And in this case, add R1 means register content R1 will be added with the accumulator, and the result will be stored in accumulator also. So only one variable or one memory content, that is register, is used, so it is called one address instruction. In the last case, zero address. Here specific no memory location will be used. So what happening here? Here SP means stack pointer. So automatically zero address instruction, or in this case add SP plus SP, that means the top two content of the stack pointer will be used and they are added, and the result will be stored in the stack top location. So these are the basically the 5 classifications, and we are going to in details how they are working actually. Start there. So we are going to discuss now the 3 address instruction format with an example. Okay, as we know, the 3 address instruction, that means 3 memory locations will be used in this case to define the instruction. For example, here we are going to execute an arithmetic expression, that is x, and the numerator part is the a plus b star c, and there is the denominator part also. Okay, so what is the preferences of arithmetic equation? So at the first case, in the numerator part, b multiplied by c will be executed and result will be stored in a. Sorry, the b and c multiplied and the result will be added with the a, and in the same way we also execute the denominator part. So at first we execute b multiplied by c. So here the example, the instruction is multiplication, that is the MUL man R1 comma b star c. Here b and c, the result will be multiplied and the result will be stored in register R1. So register R1 contains memory content of B multiplied by memory content of C. So this part is already done. Now this will be added with memory content of A. So now R1 contains the previous value of R1, that is B star C, and memory content of A will be added with it. So the whole numerator part will be stored in register R1. So add R1, A. That means A will be added with the previous content of R1. And in that way, the remaining part also done. For example, E multiplied by F, here the multiplication is done at first, then it will be subtracted from D. So E multiplied by F will be stored in register R2 because register R1 already contains the numerator part. Okay, and it will be multiplied, so E multiplied by F will be done and the result will be stored in register R2. After that, it will be subtracted from the memory content of D. So sum memory content of D minus R2, that is the current value of E star F, and it will be subtracted and the result will be stored in register R2. So the whole result is stored in register R2. Okay, and as we know, the numerator part is the content of register R1. Now the remaining part is G multiplied by H. So we multiply this and we will store in register R3. So multiplied function, the instruction is the operation code, and G and H multiplied and the result is stored in R3. So that R3 contains memory content of G and memory content of H, and they multiplied and the result will be stored in register R3. So this content is stored in register R3. Okay, now we are going to add register R2 and register R3. So here you can see R2 and R3 will be added and the result is stored in register R2. So register R2 contains the denominator. So register R1 contains the numerator part and register R2 in this case is the denominator part, and it is going to assign it the variable x. So now register R1 is divided by register R2. So division R1 and R2, and the division result will be stored in memory location x. So division x, R1, R2. So in this case, as you can see, memory content x contains division memory content of R1 and R2. The division result will be stored in x. So as you can see, the whole result will be stored in variable x or memory content of x. So this is done by 3 address instruction format. So now we are going to discuss how the 2 address instruction format works with the same example as in the previous. So here you can see the same example. So at first, memory content of B will be stored in register, some register, and memory content C will also stored in some register. Then we multiply the both. First of all, so move function, that means moving the content of memory location B to a register. So memory location B is moved in register R1 in the first case. Similarly, now the memory content of R1, that is the memory location of B, will multiply by C. So R1 contains the previous value of R1 and the memory content of C. So now R1 contains the multiplication value of B and C. So this total value B and C is contains in R1. Now it will be added with memory location A. So add R1, A. So R1, that is the value of B multiplied by C, and it will be added with A. So the register R1 contains the total numerator part R1. So in the same way, first of all, we are going to store the value of D in some register. So maybe register R2, because already the numerator part is stored in R1. So move R2, D. So the memory location D, content of memory location D is stored in memory location, so register R2. And we are going to store E in some register and F some register, that will multiply and the subtraction will be done. So you can see here, memory location E is stored in register R3 and memory location F is stored with the multiplied by register content R3, and at last the subtraction value subtracted it from the value of D. Okay. So in this way, we are implementing the 2 address instruction format. Okay. Now we are going to 1 address instruction format. With the same example. So you can see here. So 1 address instruction format means here the concept of accumulator. So here in 1 address instruction format, the concept of accumulator is coming. The accumulator, as you know, it is a temporary register which can store the intermediate value of an instruction and it is residing inside the CPU. So first of all, we are going to store the memory content of E, in an accumulator. So memory content of E is stored in accumulator. In the second case, it will be multiplied by F. So accumulator content is multiplied by memory content of F, and the result will be stored, as we know, it is stored in accumulator. Now the Now we are going to store the accumulator value, that is the E multiplied by F, in some temporary variable, because we need to clear the accumulator as the further operations will be done in the accumulator. So the accumulator content will be stored in some temporary variable t. So here store t, that is the E multiplied by F, which is stored in accumulator, is moved in a temporary variable or temporary memory location t. Now the accumulator is already empty, so the memory location or content of memory location d is stored in accumulator. So load d, that means memory location d is moved in accumulator, and this accumulator is then subtracted. So sub t, okay, that is accumulator value is subtracted from the memory content of d. So that is the sub memory content of t, that is temporary location where E and F is stored. Similarly, the result is again stored in temporary variable t. The content of accumulator is stored in temporary variable t because we need to clear the accumulator for further instruction execution. In the same way, the remaining part will be done. And ultimately at the end, here you can see the result ultimately stored in the accumulator, and it will be assigned to the variable x in the memory location. So here you can see it is named so only because the accumulator is the part of the instruction and only one memory location is used. So it is called the one address instruction format. Now in the last case, this is the zero address instruction format, and zero address instruction format means here no specific memory location will be used. The instruction execution is done by using a stack. So what is stack? In brief, we can say that stack is a data structure in which the memory location or the data will be stored in first in last out manner. So whatever the data is inserted in a stack will be removed at last. Okay? So, and the operation of inserting an element in a stack is called, we call this push operation, and removing an element from a stack is called the pop operation. And if an operand is coming, so it will be added to the stack, and if an operator is coming, then we remove the top two elements of the stack and we execute it, and the result will be then stored in the stack. In this way, the operation is done in a stack. So the same example we are going to discuss. Okay. At first, as we also know, there is a way of executing the operation using stack. For example, in this case, the whole equation will be converted in a postfix expression to use a stack. So a plus b star c, and the remaining part is using in the postfix expression. As you can see, it is expressed in a postfix expression. Okay. Suppose we are going to discuss it here using an example. Okay. So here you can see, as we discussed, if an operand is coming, operand will be stored in a stack, and an operator is coming, then we remove the top two elements, and the operation is done, and the result ultimately stored again in the stack. So here in the first case, A, so A is an operand we store in a stack, and remaining part is B and C, both are the operands where we can store in a stack. Next, the the multiplication is the operator. So we remove the top two elements C and B, and it is the operation. The operation operator becomes B star C. So it is stored in the stack again. So B star C here and C there is nothing. So it is a empty portion. So in this way, the whole operation will be done, and the ultimate and the final, the top value means the stack top position contains the whole equation, and at the finally we pop the only one location that is A. We can assign the value in the X actually. So this is why that's why in this way we can execute any operation in different instruction format. Thank you.